Yeah.
So, Prashant, do we start or wait a little bit?
Couple of minutes more.
Sure. Academic time.
Yeah.
Yes.
You talked about the similarity between Brazil and India. When I was doing my PhD in Rochester, 3 or 4 of Brazilian students like Marcos Pinto and others, and 3 or 4 Indians. We are the only people who are doing theory.
I see. Very good, yes. So you know that I got my PhD in Rochester as well.
Yeah, I know that. I know
sure.
that. Yeah. I think you had overlap with Professor G.S. Agarwal.
Yes, well, I worked with Joe Eberly for some time, and then with Moises Nussensweig. Okay, so that was it, yes.
Actually,
nice times there.
Yeah, Nussensweig used to visit Rochester and work with Wolf when I was there.
I see. Yeah, so now he's in Brazil. Yes.
His son is also in your center, is that right?
What's that?
His son is also an experimentalist, right?
Yes, that's true. That's true.
Okay. Yeah, we can start. Yeah.
We start?
Yeah.
I'm going to share my presentation. So I'm used to Zoom, so I believe that's going to work. As soon as, you have authorized me to share, right?
Right. I do think so. Avinash is around, so I'm sure Luiz has control over the screen, right, Avinash?
Yes, sir.
Yeah.
Yeah, okay, good.
Okay, so great. So let's start here. So I'd like to welcome Professor Luiz Davidovich, who is Professor of Physics at the Federal University of Rio de Janeiro. And as we just were discussing, he and our very own Prashant, both of them have done their PhDs at the University of Rochester. And Professor Davidovich has been working in quantum optics and quantum information since then. And most interestingly, he actually, he's especially enthusiastic about proposing experiments that probe subtle aspects of the quantum world, and major contributions are in the fields of decoherence, entanglement, laser theory, quantum metrology, and especially in the role of detailed role of the environment and the dynamics of quantum coherence and entanglement. So the great thing is that he himself proposes experiments, though he's mostly a theorist, but he's, of course, many of the theory he has proposed has been probably tested out in his own group as well as in Europe. And of course, he's a very, very well decorated scientist. I mean, he has been awarded the Brazilian Grand Cross, National Order of Scientific Merit, the Physics Prize in the World Academy of Sciences TWAS 2001. And presently, he's also the president of the Brazilian Academy of Sciences, General Secretary of TWAS. So yeah, obviously he's absolutely, very much up there in science administration as well, besides being such a fantastic scientist, active completely in research even now. So without much ado, I would hand the, stage or online, our Zoom platform to Professor Davidovich, and let's take a journey for the next hour or so with him. Professor Davidovich.
Thank you very much, Professor Banerjee, for this nice, very friendly introduction. I'm very happy to be in Calcutta now, even though we are both in the cloud, I guess. And I do remember the 2010 meeting on quantum optics and quantum information in Hyderabad, which was a fantastic meeting. And I'm very happy to be able to participate in this meeting now, even though it's only virtual. I would love to be there presentially. Anyway, maybe next time. So thank you very much.
We're all waiting for a next time.
Yes.
Desperately waiting for a next time. Yeah.
We are. I have been here hiding from the virus for more than 1 year now. So I want to say good afternoon to all the people who are listening to this lecture, to the students especially. And I should say that, for me, it's a good morning. It's 6:30 in the morning now in Brazil, so I had to wake up very early. I remember, people tell this about Wolfgang Pauli, that once, a student proposed to have a seminar with him at 7 in the morning. And his reply was that he would not be able to stay awake so late. So I guess that's the same thing with me. Anyway, so I'm going to tell you about some recent research, but since it's a school, I'm also going to give you a perspective on what is commonly called quantum sensing or quantum metrology. And the first step, actually, which usually makes me very nervous, is to try to share my screen. So I'm going to try that now. And you'll tell me if you can see it there. It may take some time.
Yeah, it's fine. Yeah. Quite fine.
Okay, very good. So, light speed from Rio de Janeiro to Calcutta. So that's what I'm going to talk about, quantum sensing towards the ultimate precision limits. And the outline of this lecture is the following. I'm going to focus on recent developments in quantum metrology, and the idea is to answer some very fundamental questions. First, what are the ultimate precision limits in the estimation of parameters? Second, are there fundamental limits? Is quantum mechanics helpful in reaching better precision? And third, how to cope with the deleterious effects of noise. Now, I'm going to focus on local quantum metrology. That means that one wants to estimate a parameter confined to some small range. For instance, sensing phase changes in gravitational wave detectors, or yet very small forces or magnetic fields. These are typical quantum sensing problems. Now, if you want to go in more depth in this field, you can look at the 4 lectures I gave at Collège de France in 2016. This is a set of 4 lectures that covers this area of quantum metrology. Of course, I'm going to present today some more recent results, but there you can find, say, the basics of this field in more detail that I will be able to tell you today. Now, okay, so parameter estimation is important in several fields, actually. For instance, maybe one of the simplest examples is the use of sound waves to measure the depth of an oil well. We may be also interested in the time duration of a process. We might be interested in measuring weak forces or small displacements, phase displacements in the interferometers down here, transition frequencies of atoms, and we would like to measure that with a very high precision for several purposes. And this is a fantastic example of that. You have here 2 clocks, which are actually 2 atoms in different positions, in different heights. And the difference in height between the 2 atoms is just 33 centimeters. And that brings a relative difference in frequency just because they are in different positions in the gravitational field. So that's really general relativity playing a role here. The difference in frequency is given by this expression here. So you see that people were able to measure a relative difference of frequency of the order of 10 to the minus 17. And that was done by Wineland's group at NIST in Boulder. So that's another example of some very fine measurement that gives us important information. In fact, you see that with this kind of device, you could measure gradients of the gravitational field. And of course, a very well-known example is the measurement of gravitational waves done at the Laser Interferometer Gravitational Wave Observatory, so-called LIGO. And that's a very interesting example. You see, people were able to detect here on Earth the effects of a collision of two black holes. Each black hole had about 30 solar masses. This collision took place 1.3 billion years ago. So we're looking into the deep past. And in fact, during this collision, 3 solar masses were converted to gravitational radiation in the final fraction of a second. So just imagine these waves in space-time propagating through space and getting to Earth 1.3 billion years after the collision, and then humanity was able to detect it. And because of their contribution to the design of this experiment, Rainer Weiss, Barry Barish, and Kip Thorne got the Nobel Prize in Physics in 2017. Now, in this measurement, you had actually 2 interferometers, one in Livingston in Louisiana, the other in Hanford, Washington. They could measure then signs like this one here. These are the signs corresponding to these gravitational waves. And in fact, the 2 observatories found about the same signal, but the phase, of course, because one was farther away than the other. So you could even see the propagation of these gravitational waves because of this delay between the 2 signals. They were able to measure the signals by looking at the change in the length of the arms of the interferometers due to the gravitational waves. And the differential displacement sensitivity they were able to measure was of the order of 10 to the minus 19 meters. Just compare that with the size of a proton, which is 10 to the minus 15 meters. And the relative change in distance, that is, the differential displacement divided by the length of the arm, was of the order of 10 to the minus 23. An amazing achievement. And in fact, after this measurement, people started to think about using quantum light states, in fact, the so-called squeeze states, to increase the sensitivity in the detection. And this plot here shows the effect of the noise. This line here represents the so-called short noise, and the blue region here corresponds to the gain in sensitivity due to the use of squeezed states. And the squeezed states, they have started using those in these observatories, and they allows us to increase the sensitivity and therefore to explore even further in space, which means that we'll be looking at times in the past which are even larger than 1.3 billion years ago. In fact, times like 7, 8 billion years ago have already been detected. Collisions that occurred at those times have already been detected. So it's an amazing achievement and an example of how far has metrology gone, and in fact, nowadays, how far quantum metrology has gone. Now, quantum sensing is now applied to several fields. It has been a very fast development of the field. We can use, for instance, a single atom to map the structure of a biomolecule. You see here the atom with its spin, and the spin of the atom is sensitive to the magnetic field produced by the spins of the individual atoms of this biomolecule. You can use nitrogen vacancy magnetometry. Again, the use of a spin to detect very weak magnetic fields. Magnetic sensors have been used for brain imaging. You now have gravimeters that are based on falling atoms and can be used, for instance, for oil prospecting, since oil under the the surface of the Earth will change the gravity, and this change can be detected by these gravimeters. Quantum gyrometers with a dimension of about 10 cubic centimeters, and that have a precision of 1,000 times the precision of optical gyroscopes have been developed, and also accelerometers that produce an error of 1 kilometer after 100 days. So that means that if you have a submarine, you don't need GPS for navigation. If you know the initial position and the initial speed of the submarine, of the airplane, you can find the final position just by using these very sensitive instruments. You don't need GPS. Also, satellite-based gravimetry can measure small changes in the Earth's water mass, which affect the mass distribution and therefore gravity, and that can be used for climate monitoring. So you see, it's amazing how fast this field is developing, from very basic science to very useful applications. Now, experiments in this field have been done in several labs in the last decade. I'm not going to discuss each of these papers, no time for that, but I believe you will have a copy of this presentation. I'll make it available. So if you're interested, you can go through these papers. So people have been looking at phase resolution. They have been looking at atomic clocks. They have been looking at magnetometers, like those that I have already mentioned, with some recent papers on magnetometry with nitrogen vacancy centers, for instance, nuclear spin-assisted magnetic field angle sensing, which could be interesting for detecting rotations, for instance, and so forth. So it's a fantastic development. Sensitive measurements of force, displacement, and small tilts of mirrors have already been demonstrated. Our group has done experiments on that. This is just one example of an experiment with some fancy words. It's quantum enhanced sensing from hyperentanglement. There is also collaboration between our group and the group of Serge Haroche at Collège de France. And there we have also demonstrated experimentally the measurement of a small microwave field beyond the so-called standard limit, therefore with quantum metrology in action. So you see, many experiments have been done. But besides the possible applications of quantum metrology, there are also some conceptual interesting results which have to do with going beyond Heisenberg uncertainty relations. You may remember this Heisenberg uncertainty relation, general kind of uncertainty relation, in which you have two operators, A and B. You can find the commutator between these two operators, and then the product of the standard deviations, so the square roots of the variance of these two operators, is bounded below by the magnitude of this commutator divided by 2. So this is just the general Heisenberg uncertainty relation, but then people have asked some very fundamental questions about the meaning, say, of time-energy uncertainty relation. How can you understand that, since time does not have an operator associated with it? Energy, yes, but not time. You don't know about time operators. What about number phase uncertainty relation? Of course, the number of photons, you can associate an operator to that, but the phase, people have devised some phase operators. There are very frequently some mathematical problems with that. Now, can you give some general meaning to this number phase uncertainty relation? And what I'm going to show you is that, yes, you can. Quantum metrology allows one to give another interpretation to the time-energy uncertainty relation and also to the number phase uncertainty relation. So these are the questions that we want to address. And now I go back to the basics, to parameter estimation in classical and quantum physics. So the idea is that you have some dynamical process that depends on some parameter that you want to estimate. And so you get here a probe. You know the initial state of the probe. You send the probe to the dynamical process, or if you want, you have it interact with this dynamical process. So the probe changes its state, and then you measure the final state. And from the measure, you get an estimation of the parameter. So these are the steps: prepare probe in suitable initial state, send the probe to the process to be investigated, choose a suitable measurement, and associate each experimental result, say psi, which is a random variable that may have several components, with an estimation of the value of the parameter through some estimator, which I represent by this expression. So the estimator is just a function that, given the measurement results, gives you an estimation of the value of the parameter. Now, we need a merit quantifier, something that allows one to say how good was the estimation. And the usual merit quantifier is given by this expression, is the standard deviation between the estimated value of the parameter and the true value of the parameter. Now, you may well ask, come on, I mean, how can you calculate this merit quantifier if, after all, it depends on the true value of the parameter that you don't know? So what happens is that usually one deals with unbiased estimators. And for an unbiased estimator, the average of the estimated value coincides with the true value of the parameter. If you have a biased estimator, that's a bad estimator. The average will give you something different from the true value of the parameter. And an unbiased estimator is defined by this first expression here. The average should be equal to the true value of the parameter. And also that should hold in the neighborhood of the true value of the parameter. That means that this derivative here is equal to 1. Now, if this is true, then we can replace x true here by the average value of the parameter. So this merit quantifier becomes what we call the standard deviation of the estimation with respect to the average number of the parameter. So it's the quantum, it's the standard deviation of the estimation. And then I replace this symbol here by this big delta symbol. And from now on, this big delta symbol means standard deviation, the square root of the variance. So the field of metrology owes a lot to these three guys here, Cramer, Rao, and Fisher. And they showed that the standard deviation of the parameter is bounded below by this expression here. Nu here is the number of repetitions of the experiment. It just tells you that if you repeat the experiment many times, you get a better precision. And then you have this function here, which depends on the true value of the parameter, or if you want, on the average value of the estimator. And this function is given by this expression here. It's a funny expression. You see that this P of psi x is just the probability density of getting an experimental result psi if these experimental results form a continuum. Or then you could have this expression here for discrete experimental results. So either an integral or a sum. And you see that you have here the, this big D here should be small d. So you have the derivative of the probability with respect to the parameter squared divided by this probability. Now, this expression here for the continuous case, or this expression here for the discrete case, is called the Fisher information. And in fact, the Fisher theorem showed that this inequality here can actually be saturated. That is, it is possible to make it an equality when the number of repetitions goes to infinity by choosing an appropriate estimator, x. Okay, so this is the basics of quantum metrology, and that, of course, was first applied to classical metrology. Now, what about quantum parameters estimation? Well, there are new points to consider. First, the precision in the determination of a parameter depends on this distinguishability between quantum states corresponding to nearby values of the parameter. Let's understand this. So that means that if I change the parameter a little bit, if the state changes a lot, that means that you'll have better precision in the estimation of the parameter, because it will be easier to distinguish the first state from the second state. So that's the first point to consider. Second point is that, in quantum mechanics, the measurement process is very important. Measurement matters. And usually you have a choice of different possible measurements, and maybe some measurements will give you better precision than other measurements. Third point, is it possible to get a better precision for the same amount of resources by using special quantum states? So can we profit from the freedom of quantum mechanics to get a better precision? And I should define what I mean by resources, and that depends very much on the system under consideration. Resources could be the number of atoms, say, in atomic spectroscopy, the number of photons in optical interferometry, the average energy of a harmonic oscillator, and so forth. So for each problem, we must define what we mean by resources. Now, let me give an example of how this distinguishability between quantum states helps to estimate a parameter. Now, let's start with a coherent state. I assume you know what a coherent state is, and in fact, I just remind you that a coherent state can be expressed in terms of Fock states, that is, number operator eigenstates. You can think about a harmonic oscillator, for instance. And the coherent state can be expressed in terms of Fock states in this way. Now, suppose now you have an interferometer like this. This is the input doors. There are two doors here. This is a phase to be estimated, and these are the output doors. Now, we want to estimate this angle theta. Let's suppose that this angle is very small, so delta theta. And then I want to calculate the scalar product squared between the original coherent state and the coherent state with this phase delta theta, so the dephased coherent state, or the coherent state with a shifted phase. So this scalar product can be very easily calculated using this expression here. It's given by this expression, and if delta theta is very small, I can approximate this exponential and get this expression here. You see this is a Gaussian in delta theta, and from that, you can get an idea of the precision in the estimation of delta theta, since it's a Gaussian. So the width of the Gaussian is 1 over square root of the average value of n. So delta theta, the precision should be given by this expression here. So you see that we get the precision from this scalar product here of two states. And this scaling here, proportional to the square root of the average number of photons, which is the resource in this case, is called the standard limit. Okay, so that's the standard scaling in the estimation of phases. And here I'm ignoring repetitions of the experiment. So I'm just talking about a single experiment. So can we do better than that? Yes, we can. And this was shown by David Weiland and collaborators, and also by Jonathan Dowling. You can, for instance, use the so-called Noon state. And the name of the state is due to this representation in terms of Fock states. So this is a superposition of two states, one which has n photons in the upper branch, or the lower branch, the other which has n photons in the upper branch. Now, when this goes through this interferometer here, you see that only the upper branch gets phase shifted. So this state becomes this state here. You see, if we look at this phase in the upper branch. You should also remark that now I don't have just theta, I have n theta because there are n photons in the upper branch. And now we can find the scalar product between psi of n and this phase shifted psi. And that's very easy to calculate. I leave to the students to do that. So that's given by this expression. And this is equal to 0 for delta theta equal to pi over n. So now you see that the uncertainty in the estimation of the phase scales as 1 over n, which is much better than 1 over square root of n for the same average number of photons. So this is the so-called Heisenberg scaling. It shows that this Noon state is more sensitive to phase changes than a coherent state. So you see how the sensitivity of states is very important in the estimation of parameters. Now, let's make it more precise, and based on the classical definition of Fisher information, let's now define the quantum Fisher information. So the quantum Fisher information is defined in a similar way as the classical Fisher information. You have the same kind of expression here. You see the derivative of the logarithm will give me just dpdx squared over 1 of p squared. So you get the same expression as we found before. So this is just the classical Fisher information expressed in terms of this probability. But this probability now depends on the kind of measurement you do. So quantum mechanics tells us that the probability of finding an experimental result psi, if the value of the parameter is x, is given by the trace of this operator, which is a measurement operator, in the density matrix of the system. Now, these operators, more simply, are the so-called von Neumann measurement operators. In a more sophisticated way, they don't have to be orthogonal, they don't have to form an orthogonal set. And in the general case, they are called positive operator valued measurement operators. And they have to satisfy this completeness relation. That means that you are doing all the measurements you can do, but choosing a set of measurement operators. And of course, you have some freedom in choice. You can choose several sets of measurement operators. So this corresponds to a given quantum measurement. Now, the ultimate lower bound for the variance in the estimation is given by optimizing this expression over all possible measurements. And this maximum of the Fisher information over all possible measurements is called the quantum Fisher information. So it looks, I'm talking to the students now, it looks like a nightmare. Huh? Come on, I mean, you have to calculate not only the Fisher information now, but you also have to maximize it over all possible measurements. Same stuff. Now, if you have the maximum value of all the Fisher informations, then that will give me the minimum value of the bound. So I can say that the precision in the estimation of the parameter x, if you understand the deviation in the estimation, is bounded below now by this expression here, which has the quantum Fisher information in the denominator instead of the Fisher information. So since this is the maximum of all the Fisher informations, this corresponds to the ultimate precision limit in the estimation of the parameter. And Fisher showed that this is asymptotically attainable when the number of measurements goes to infinity. Now, one might ask, can I interpret this Fisher information, this quantum Fisher information, in some sensible way? What is the meaning of the quantum Fisher information? And indeed, there is a very nice meaning to it, which can be expressed in terms of the so-called Buer's fidelity. What is that? Well, that's the fidelity between two density operators. It is given by this expression here. Looks like a fancy expression, but that's now an exercise for the students. Suppose rho 1 and rho 2 are pure states. So show that this expression reduces to this one, which is just the magnitude square of the scalar product between psi 1 and psi 2. So you see, this is the generalization for density matrices of this expression here, which is well known as an expression of fidelity. So the intersection, if you want, between two states of the system. Now, it can be shown that if you calculate the fidelity between the density operator of a probe that interacts with a dynamical system, it corresponds to some density operator if the value of the parameter is the x true, the true value of the parameter. So the fidelity between this density operator here of the probe and the density operator for another value of the parameter, which is different from x true, if you expand this expression of the fidelity as a function of the distance between x and x true, you find this expression here. And in the lectures I gave at Collège de France, you can find the derivation of that. Now, that's a very interesting expression because it shows that the first contribution is squared in the distance between x and x true, and the coefficient of delta x squared is just the quantum Fisher information divided by 4. And then you have higher order terms here. So you see, that shows that the quantum Fisher information is indeed related to the distance between these two states measured by the fidelity. If delta x as delta x goes to x true, or I beg your pardon, when delta x goes to 0, when it is infinitesimally small, you get this expression here. So in some sense, you can show that the square root of this expression here, which multiplies delta x, is the speed of separation between the two states as x changes from the true value of x. Okay? So this is related to what I told you before. The quantum Fisher information is related to the distance between states. And the larger the quantum Fisher information, you see that the fidelity will be smaller because there is a minus sign here, which means that the rho of x will be more different than rho of x true. So it will be easier to distinguish the difference in the parameters. And therefore, the precision in the estimation of the parameter will be higher. Okay? So very important expression. And please remember this statement here, that the square root of the quantum Fisher information divided by 4 is the speed of separation between the two states as the parameter changes. Of course, I'm using speed here in a generalized sense. If this parameter was time, then of course it would be the real speed, but it can be anything. And so it's really the speed of separation as with respect to the parameter in question. Now, as I mentioned before, it looks tough to find the quantum Fisher information as a maximization of all Fisher informations over all possible measurements. However, this can be done for pure states. And Hellstrom showed in 1976 that the quantum Fisher information for pure states and for unitary evolutions is very simple. And just remember, when I talk about pure states, I'm talking about pure states of the probe that is investigating the dynamical process. And also, I'm assuming that the interaction between the probe and the dynamical system leads to a unitary operation on the probe, okay? So what Hellstrom showed was the quantum Fisher information was given by this very simple expression, 4 times the variance of this operator H, the variance calculated in the initial state of the probe. And this operator is given in terms of this unitary operator by this expression here. So let me give an example. Suppose this unitary operator is given by this expression here, exponential of I, some operator O times X, where X is the parameter you want to estimate, and O here we assume that it's independent of the parameter. Then you plug this U of X into this equation, and you find that in this case, this operator is given by precisely this operator here. So this, if X was the time, O would be the Hamiltonian. Okay, but this is if you want a generalized Hamiltonian, it does not correspond to energy, it does not correspond to, and X does not correspond to time in general. So if this is so, then if the quantum Fisher information is given by this expression, Then using the Cramer-Rao expression we had before, you see that the precision in the estimation of the parameter, or the standard deviation of the parameter, is bounded below by this expression here, where this is the variance of this operator here, which is technically called the generator of the unitary transformation U of x. Now, you see, if x was the time, this would really look like the time-energy uncertainty relation. But of course, time here would not be an operator, time would be a parameter. And that's the very important difference between what I'm telling you today and about some other people talk about the, say, energy time or number phase uncertainty relation. Okay? So, Hellstrom helped us to overcome the nightmare. For pure states, it's easy to calculate the quantum Fisher information. So let me give an example of parameter estimation, simple example of spatial displacement. So suppose you have some object here, and this is actually the wave function, or if you want, the representation of the state of the object in the phase space. You know, classically, this would be momentum vertically, horizontally would be the position. And then you submit this object to a translation. And remember, spatial translation is given by this unitary operator here. P is the momentum operator. X is the parameter that quantifies the displacement. X is not the position operator. X is a parameter. And I want to estimate this parameter, which will be able to give me some idea about how far this object has gone. So using the expression I gave you before, I can calculate the generator of this transformation. And indeed, this expression will give me the generator of this displacement transformation is the momentum operator. And then, thanks to Hellstrom, the quantum Fisher information can be calculated, and it is given by 4 times the variance of the momentum. And due to the Cramer-Rao relation, I can now write the standard deviation in the estimation of this displacement here, which you have here, by this expression here. So again, look at this expression here. Take delta P and take it to this side of the equation. You see that that looks very much like the position-momentum uncertainty relation, but it is not, because X is not an operator. X is a displacement, is a parameter. And also, you see that the uncertainty in X depends on the number of times you repeat the experiment, which is not the case of the uncertainty relation, right? Okay, so this is for this kind of representation of the state in phase space. Now, can we do better than that? Well, we can. You see, if we had a coherent state, the variance of the momentum for a coherent state would be equal to 1 over square root of 2. And that would give me a standard deviation for the parameter given by this expression here. So in the case of spatial displacements, this is the so-called standard quantum limit. So the standard quantum limit is not always 1 over square root of n. That's true for phases. But for displacement, the standard quantum limit is just this. Is 1 over square root of 2 for one measurement, for a single measurement. If you have new measurements, then you do have the square root of new underneath. Now, can we do better than that? Well, we can use a squeezed state like this one. You see, in phase space, if you represent a squeezed state in this case, you see that delta X is smaller here. The uncertainty in if you want the width of this state. However, delta P increases, so the variance in the momentum increases. And if you do that, it's clear that you can have a higher precision in the estimation of the displacement just because this width here is smaller. So the uncertainty will be smaller. And in fact, with this expression here, you see that if you increase the variance in the momentum, you decrease the uncertainty in the estimation of the parameter, which in this case is the displacement of the state. Okay, I think that's a simple example which gives you the flavor of quantum metrology. Now let's go back to optical interferometry again. And we have again the interferometer. And let's look then for the generator of phase displacements. And that's the number operator. How can you know that that's the generator of phase displacements? Well, just apply this exponential here. Here you have the number operator, A daga A, and the angle theta, applied to, say, a Fock state. Now, because you have a Fock state here, the number operator here becomes just N. So this is equal to that. And you see that, in fact, this number operator here was the generator of this phase displacement here of the Fock state. If you apply it to a coherent state, then you have to apply this expression here to each component of this expansion here. And then I leave to you to demonstrate that this exponential applied to a coherent state gives me this expression here, and therefore it indeed displaces the phase of the initial coherent state. Okay, so that's the generator of phase displacements, and that means that the quantum Fisher information in this case is equal to 4 times the variance of the number operator, where here, since the phase is only the upper arm, that should be the variance of the photon number in the upper arm. Now, the standard limit is obtained for coherent states again. For coherent states, the variance in the photon number is equal to the average photon number. And by plugging this into the Cramer equation, I have this expression here. So this is the standard limit, now precisely defined in terms of the quantum Fisher information. And again, if you use known states, then you find, using the same scheme here, that the precision is bounded below by 1/n, which is the Heisenberg limit, much better than this, take n equal to 100. This will be 1/100. This will be 1/20. So much better with known states. Now, some years ago, we asked the question, how can we generalize these procedures to systems that have decoherence, to systems that are interacting with the environment, that are subject to loss of coherence, subject to noise. And in fact, noise can have a very bad effect on all of this. The loss of a single photon, for instance, transforms the known state into a separable state. Because if this state here loses a single photon, well, if it is in the upper branch, you'll know, because the photon will leave, and you'll know that from that upper branch, and you will be able to detect, therefore, that there was a loss of a single photon. So you know that after that, the state will be this one or this one, after the loss of a single photon. And this is not a superposition anymore. For those who know about mixtures in quantum mechanics, this is actually a mixture of this state and this state. You can get either one of the two. And therefore, the known state is very quickly destroyed and transformed into one of the states. The loss of a single photon is enough for that. And this explains why known states, which are very effective without losses to have a precise estimation of the parameter, are now very, very bad, because they are transformed into Fock states, and Fock states don't give you any information on the parameter just because they acquire a global phase, and global phases cannot be measured, okay? So now there is a general formalism for estimation of parameters with losses. Because of lack of time, I think I'll jump over this, and I'm not going to discuss this. You can find them in the copies of the slides. But in what I can say, and I just show you the slide, just to convince you that it's usually very difficult to calculate the quantum Fisher information for processes with losses. Basically, what you have to do is to diagonalize the density matrix of the probe. And if you are dealing with a system with a very high dimensional density matrix, this could be a very hard task. So we decided to look at this problem from a different angle. And this was explained in these two papers here. So the idea is the following. Given some initial state in a non-unitary evolution, we define in the system plus environment set a unitary evolution. So, the trick is the following. You have a system interacting with an environment. So the system is an open system. It is subject to decoherence. It is subject to noise. So we include the environment into the description. So that system plus environment is a closed system now. And you define now a unitary evolution in this full system. It's now unitary since you have a closed system. And this is called the purification of the initial state. And this unitary evolution is defined in such a way that if you trace out the environment, you will have the dynamical evolution of the system without the environment, so which is expressed by a density matrix, okay? So that's the idea. So that's the purification of the evolution of the system, which is described by, say, a master equation with density matrices and so forth. Now, if you have this purification, then we can now calculate the quantum Fisher information for the whole thing, because it's a closed system. There's a unitary evolution. The trick by Hellstrom applies. So we have a closed expression for the quantum Fisher information in this case, which is obtained in this way. Look at the right-hand side of this equation. So it's the maximum over all possible measurements on the whole thing of the Fisher information of the whole thing. And this gives me this quantum Fisher information for the whole system, which is proportional, to the variance of the generator of this transformation here. But you have to maximize it over all possible measurements. And you know that this is 4 times the variance of the generator. Now, since I'm measuring over all system here, this maximum should be higher than this maximum here of the Fisher information that corresponds to measurements on the system alone, because I have less freedom here. So here, I'm just measuring the system. I'm not doing anything on the environment. That's the rule of this identity operator here. And I'm maximizing the Fisher information over all possible measurements on the system alone. Now, this should be, in general, smaller or at most equal to this quantum Fisher information for the whole thing. Since here, I have more measurements to deal with. I can measure over the whole thing. So this is the fundamental inequality which we use to find upper bounds to the Fisher information of the system, an open system. Okay? And this happens to be actually very, very helpful. So the physical meaning of this bound here is that it relates to the information obtained about the parameter when S plus E is monitored and not just S. And of course, we are interested not just in calculating some upper bound, but we are interested in calculating the minimal upper bound, because that should be closer to the quantum Fisher information of the system, which we want to calculate. So we want to calculate the least upper bound, which means minimizing this expression here over all unitary evolutions in S plus E. And that should be a difficult problem. Now, what we showed in this paper is that this bound here is actually attainable. In other words, there is always a purification such that this bound coincides with the quantum Fisher information of the system. Just for the students so that they know how these things go, we first submitted a paper, we submitted a paper to Nature Physics, and the referee told us, well, if you could show that this bound is attainable, then the paper would be acceptable. So we had to work more and we showed that, so it was accepted. So the physical meaning of this result is that in this case, monitoring S plus E use the same information as monitoring S alone. Now I see that Werner has a question now, and please answer. Please ask your question.
Good afternoon, sir. Sir, actually,
Good
I
afternoon.
wanted to know when you say that minimize over all the unitary evolution, wouldn't that only be a single unitary evolution that will be used to move along a single parameter that we are talking about in the whole system?
Okay, very good. So, yeah, you can actually have several unitary. Very good question. You have several unitary evolution. You may have several unitary evolutions that will lead you to the same dynamic evolution of S. Okay? You can show that the several unitary evolutions are related by unitary transformations in the environment alone. Okay, that's an interesting result that is known in quantum information. But your question is, if I understood it correctly, the answer is yes. There are several possible purifications for a master equation evolution, but they are all related by unitary evolution, by unitary transformations on the environment alone. Have I answered your question?
Sir, yes, sir, but I have one more doubt in this. If I see the Hellstrom equation, that is du dagger by dx and then u itself. So if I take the whole system and then take a pure state, if I take different unitary evolutions, they will only differ if I have a different generator along the parametric path.
Yes.
So are we saying that these unitary evolutions are due to different generators that we have along a different path on the same parameter?
Very good. So yeah, very good. So again, yes. So you see, the difficulty is even more than before, I could say, because you are right in asking that question, and the answer is yes. You can have several generators. And in fact, the work is the following. You should look for the purification that gives you this result here, okay, that attains this equality sign here. And in general, that's not a simple problem. However, what I'm going to show you is that physical arguments, physical intuition may help you to find the correct purification or the most favorable purification. So that's the idea, okay? You are absolutely right that, different evolutions can give me different generators. And the question is then, how do you find the good purification then? How can you choose the best one? What I'm going to show you is that is guided by physical intuition. And that comes in the next example I'm going to show you. Okay?
Thank you, sir.
So let me give you an example, very simple example, and I think pedagogical as well. And that has to do with the estimation of a damping constant. It's based on this paper here, which was published last year. You see one of the authors was also teaching a lecture in this school, my friend Girish Agarwal. And that's a paper on the estimation of damping constants and temperature of open systems. Now, here I'm going to talk only about the estimation of damping constants. So I want to estimate this damping constant, and I'm going to use light, which goes through, say, a transparent slab. And by measuring this light, I want to estimate this damping constant. Now, the dynamics of this probe, the light, if you want, is given by this master equation here. A and A dag are the annihilation and creation operators for photons. And that's the usual master equation that depends on the damping constant here. Now, how can we purify this system? Use physical intuition. You see, we can, instead of dealing with this open system, we can deal now with a closed system. And I do the following trick. I have here a beam splitter, and you see the beam splitter plays the role of this damping because it will reflect part of the light and transmit the other part of it. So light will be damped because just part of it will be reflected. And if you look at the whole thing here, this is a closed system. Now, you can show that if you just look at the transmitted light here, you'll get precisely this master equation, as long as you take the transmissivity of the beam splitter equal to square root of this eta here, and eta is defined as the exponential of -2 gamma t, where gamma is the constant I want to estimate, and t is time, okay? Now, reflectivity then is given by this expression here, as is usually in a beam splitter. These are the incoming fields, these are the outgoing fields, and I'm interested in the case in which the incoming field in this input door of the beam splitter is just the initial state of the probe, of the light, if you want, of the photon, if you want. And the incoming state in the other door is just a vacuum. And it's an exercise for the students. I know that you have a tutorial late afternoon, so you can try to show that if you calculate indeed the density operator corresponding to this outgoing field here, obtained by tracing out the field in this mode B here, will satisfy this equation, okay? Very nice purification. And now I think that's a way to answer the previous question, right? Because you see that among several possible purifications, I have chosen this one using a physical argument, that in fact a beam splitter is equivalent to a damping if you trace out the mode B. So that's the idea. Now, you can also use, if you want a Heisenberg picture, you can express the outgoing fields A and B in terms of the incoming fields. And that's the usual beam splitter transformation. Okay, that's true classically. If you take out the hats from the operators, you have a beam splitter transformation. And you have also a unitary transformation corresponding to the beam splitter, which produces these transformation equations here, and unitary operator transformation is given by this expression. Again, exercise for the students show that if you apply this unitary evolution to the incoming field operators, you obtain this expression here. Now, I had another question, and please, you may ask this question. I like questions being asked along the talk. Yes? No? Okay. But, please feel free to ask questions about each slide if you don't understand it. Okay? So this is the purification, and this is the unitary evolution corresponding to this purification. So now I have a generator here, you see? Now, phi is I have not told you what is phi. Let's see. Phi is given by this expression here, okay? So phi depends on eta, which depends on gamma. So this is the dependence on gamma. And by deriving this unitary evolution with respect to gamma and applying this expression, I get the generator. And if I get the generator, I get the quantum Fisher information corresponding to the whole system, to the beam splitter, including both modes. Okay? That's the quantum Fisher information corresponding to the whole thing. And I know that that should be an upper bound to the quantum Fisher information of the system alone, if you want, for the mode A alone. Now, from this expression here, I find this lower bound for the uncertainty in the estimation of gamma. You have to do some calculations. Again, a nice exercise for the students. You can get, of course, some strong hints from this paper here. But, if you want to get more familiar with these techniques of quantum metrology, just go through this paper here, at least through the first part, which is about damping, so that you get familiar with the calculations. So by using this, I get this nice expression for a lower bound for the uncertainty. It depends on gamma, it depends on time. What is time here? Times is the time it takes for the probe to interact with the system. Okay, so it's the interaction time between the probe and the system. And that's the expression. And in here is the average number of photons in the incoming field. Okay, so everything is defined here, and that's the expression, lower bound for the uncertainty. So question, is this lower bound achievable? And if so, for which incoming state? what's the best incoming state for measuring dissipation? And this is also related to the question which was asked a while ago, because of course, this is just one of the possible purifications. I could have several ones, but this is the simplest one given by physical intuition. And the question is it really the good one? Now, in order to answer this question, we can do two things. One of these things is to calculate the so-called sensitivity, which gives me the standard deviation in the estimation of the parameter gamma through this quantum error correction formula, basically. So you take the standard deviation of the outgoing photon number and divide by the derivative with respect to gamma of the average number of photons in the outgoing field. And if you do that, you can calculate n alpha from these expressions here. So you see that's the definition of the average number of outgoing photons. That's the variance of the outgoing photons. And if you do this calculation using this expression, it's a simple calculation. It's an algebraic calculation. You find that delta gamma is given by this expression. If you remember the expression I gave you before, you see that if delta n int, what is this? This is the variance in the number of photons in the incoming field. If this is equal to 0, I get precisely the expression I had before. So this gives us a hint that the best states to estimate the damping constant are Fock states. States with a well-defined number of photons so that the variance of the incoming photon beam is equal to 0. And that is also hinting that the purification I chose is the best one, is one of the best. Maybe there could be others. Because if delta n is equal to 0, that really gives me the expression I had before for that upper bound for the quantum Fisher information, of, if you want, the lower bound for the estimation of the damping constant. Well, we can go ahead, and I'm not going to go through these calculations. It will take me too far. It is possible actually to calculate the quantum Fisher information in this case by considering Fock states, incoming Fock states. Then, this master equation simplifies. If you start with an incoming Fock state, that means that there are no coherences. And since you have damping, coherences cannot be built. So that means that the density matrix is diagonal in the Fock state basis. There are not non-diagonal elements. And you can solve the density matrix precisely. And if you do that, you can calculate the quantum Fisher information in this case. No, don't pay too much attention to the details. And we are very glad that we get then that the uncertainty estimation of the parameter is precisely given by this quantum Fisher information calculated for Fock states, for incoming Fock states, is precisely the one I got before with the purified system. Great, huh? Great. 5 stars, huh? We're very happy when we found that, because that means that purification we did was actually the best one of the best ones. Maybe there is another one, but that one was useful in getting the quantum Fisher information of the system. We first found an upper bound, and now we demonstrated that this upper bound is achieved if we use incoming Fock states. And using incoming Fock state doesn't mean that you have to use a Fock state n. It's equivalent to use a stream of single photons, and we show that in that paper that I mentioned to you, okay? So the best way to measure a damping constant then, with the largest possible precision, is to send a stream of single photons. And it's very interesting that if you have some thin slab, so the interaction time is small, and if it's a sensitive device, a sensitive sample, so you don't want to have intense fields to sample that damping constant, this is the ideal thing to do. You just send single photons, and from that you get an estimation of the damping constant, which is the best one you can get. and which is given here. Okay. Now, if you look at this expression, you see that this goes to infinity when t goes to 0 or t goes to infinity. It's very simple to show that here. And you might ask, what's the physical meaning of that? You know, and it's very simple to understand that. When delta gamma goes to infinity, when t goes to 0, that means that there was no interaction between the photon and the sample. The interaction time is 0. And if the interaction time is 0, you don't have any estimation for the damping constant. That means that the uncertainty on the damping constant is infinite. Okay? On the other hand, if the interaction time is infinite, since it's a damping constant, there is no field to measure after the sample. Okay? The field is completely damped, and therefore you don't have any information as well. So the uncertainty in the damping constant also goes to infinity. Okay? So this, I think it's a nice example of when the bound works. And there are other examples as well, but I think my time is over, and I may still mention that if I have some extra time, but I'll just jump over the slides. So we have also done some work on quantum limits for lossy optical interferometry, using the same kind of idea, which I just mentioned here without giving you the results. So we have some optical interferometry with damping, and we replace the damping here by a beam splitter. So now we have a closed system, and now we intervene on the environment. The environment is this mode here, and we make a phase shift on the environment. Why? Because the idea is that, you know, if you saturate that upper bound to the quantum field information, that means that you don't get more information on the parameter by measuring the whole thing. Measuring the system or measuring the system plus the environment gives you the same information, which is the quantum field information for the system. So in order to do that, you have to erase any extra information the environment has on the parameter you want to investigate. So if you have an interferometer like that, you have the environment, which is this mode of the beam splitter. I make a displacement on the field in the environment, and the displacement depends on some phase displacement, phase shift if you want. And this phase shift depends on an unknown parameter, which for us is a variational parameter. And then we calculate the quantum field information of the whole thing, and we minimize it with respect to this parameter, so as to get closer to the quantum field information of the system. And by doing that, we find an amazing expression. I am not going to, well, you know, I'm very tempted. So yeah, I'm going to show you the results, okay? So it's a very simple result that we get by purification. Remember, purify, change, phase shift the environment, the field and environment, with some unknown phase. Consider this unknown phase as a parameter, a variational parameter. Minimize the total Fisher information, quantum Fisher information, by using, with respect to, by changing this theta prime. So you minimize it. So by minimizing it, you get it closer to the quantum Fisher information of the system. And that's what we get. So this we get from the quantum Fisher information for the whole system. And we find that the uncertainty estimation of theta is bounded below by this expression. Eta is just this damping constant here. And the expression is very interesting because you see that if the average number of photons is, I mean, this is this kind of state here. I don't want to go into this state. These are states with well-defined photon numbers. If the photon number n is sufficiently small, so it's smaller than eta over 1 minus eta, it's very simple to calculate this. So this can be neglected with respect to 1. And we find that delta theta is bounded below by 1 over n, which is the Heisenberg limit. So the Heisenberg limit is achieved in the estimation of the phase for a small number of photons. On the other hand, for large number of photons, this term will prevail over 1, and you get the delta theta is bounded below by a number that scales as 1 over square root of n, and that's the standard limit. So that means that for n sufficiently large, the standard limit, 1 over square root of n, is always reached, okay? So no matter how small the dissipation is. And that's the result we got in this paper here in Nature Physics. So now let me go very fast over all this. I'm not going to tell you about time energy uncertainty relation. And I'm just going to comment about what I have just told you, the summary of what I have told you. So what I have shown you is a general framework for the estimation of parameters in noisy systems, based on an expression of the quantum Fisher information for a purified evolution in extended space, and also on the control of the environment. So we have to change the environment through unitary transformations, using physical arguments, if possible, so as to minimize the quantum Fisher information of S plus E, so that it gets closer to the true quantum Fisher information of the open system. Now, this allows analytical calculation of very good bounds on the limits of estimation. Very frequently, we don't get the precise quantum Fisher information, but we get a very good bound, which is very close to it, and we have verified that through numerical calculations. So this bound we have obtained for several kinds of systems, for optical interferometry, for atomic spectroscopy, minimum evolution time of open systems, that's related to the time energy uncertainty relation, force estimations, dissipation constants, and temperature. Thank you very much for your attention, and now I'm ready to answer questions you might have. So I stop sharing my presentation, but you're welcome also to ask about some slide if you want. Thank you.
Yeah, thanks, Professor Davidovich, for this extremely, enlightening talk and this great journey that you've taken us through. So yeah, we had a couple of questions during the talk by a student. So so please come up with more questions. So raising hands would be useful, but presently I do not see any hands. So questions?
Yeah, can I ask one question?
Sure, please, Prashant.
Yeah. Professor Davidovich, very nice talk. I have a question. There were some papers for Jurek where he pointed out that using this cat and kitten states, particularly kitten state, you can, get this Heisenberg limit. Is there any connection of those kind of states with the method which you are showing here?
Yes, very good, very good. Yeah, sure. You can actually use dig states, you can use entangled states actually to increase the precision. And in fact, we have shown experimentally in, dig states are entangled states. That's why I'm telling you about entangled states in general. And in fact, we have shown experimentally, that's one of the papers I have mentioned to you in our lab in Rio de Janeiro, that you can, for instance, suppose you have an interferometer, and one of the mirrors in the interferometer has a small tilt, and you want to estimate the small tilt. Now, we have shown that if you use what we call hyper-entangled states of photons, you can have a much higher precision in the estimation of these tilts than by using usual light, okay? And what is a hyper-entangled state? You have two photons, which are twin photons, and they are entangled in both momentum and polarization. So they are entangled in two different spaces, the momentum space and the polarization. And we have shown that this hyper-entanglement, as we call this, indeed leads to higher precision. But in a very appreciated way. So we got actually beyond the quantum standard limit towards the Heisenberg limit in this case. So yeah, it applies to that. Of course, I have not mentioned entangled states in this talk for lack of time, but this has been demonstrated experimentally, actually. Thank you for your question.
Other questions? Students?
Well, Shivans Verma had some questions.
Yeah, he had asked some very nice questions during the talk.
Yeah, sure.
Shivansh, any other questions? Is he around?
Yes, sir. Actually, I was having one more question.
Yeah, please.
Very good.
So when we say quantum Fisher information estimation, that's generally a linear approximation theory that we are using there. So the generators that can be there can either be functions of the generator of that phase, or the direct that function itself, or or some combination of that, but they can only be in linear combination. So does it boils down to only finding the states such that they show the minimum of the minimum upper bound, or it also turns out to choosing the system or the representation from a system to the system plus environment?
Okay, so let me see if I understood your question well. First, you are right that corresponds to that quantum Fisher informations are expressed in terms of the generator of a transformation, and they measure the distance between states in the first approximation. It's not linear in the parameter; it's squared in the uncertainty. As I have shown you, if you expand the fidelity in terms of the distance between in terms of the uncertainty in the parameters, the distance between x and x true, as I mentioned that, the first term is 1, of course, because if x is equal to x true, the displaced density operator is equal to the original 1, to x true, so the fidelity is 1. And then the difference is the delta x squared term, and that comes with the quantum Fisher information. So it's an expansion, and the quantum Fisher information comes from the quadratic term there. Okay. Now, yeah, I'm not sure that was your question, but I have a question also related to that. Now, what happens in cases when the quantum Fisher information vanishes? And I have found cases like that. Okay, it vanishes. So can we go to a higher approximation? Can we do a correction so that you can find the distance between these states in a higher approximation, not just in second order, but in fourth order, say? Okay. I believe you can, okay, but right now I have been thinking about it, and I cannot give you an exact answer to that, okay? But it's true that what we have done for measuring this distance between the state corresponding to the true value of the parameter and the state corresponding to some other value of the parameter, this distance corresponds to the quantum Fisher information in second order, in the difference between the two parameters. And can we go farther than that? Maybe, and I am interested in that problem. If I have not answered your question, please ask it again.
Thank you, sir. Sir, it is partially answered. Only one part I wanted to clear was, there are two things. One is to choose the generator to find the Fisher information, and other is to then choose the representation. Both are related because if I have a system which is interacting, then I need to choose a representation of system plus environment, and then choose the generator likely there. So do we only choose the generators which are the linear functions, or it can be functions of the generator itself?
Oh, okay, good. Yes, they can. They can be, okay? No, I gave you an example of a unitary transformation, which was just exponential of I times the generator times the parameter. And I assumed in that example that the generator did not depend on the parameter. That's not the general case, okay? The general case involves a dependence of the generator on the parameter. And there are several examples of that. Yes, and that's, of course, since it's the general case, it's a very important situation. I just gave you a simple example, but in general, it does depend on the parameter.
Okay. Thank you, sir.
Thank you for the question.
Yeah, other questions? Luiz, I have, well, I'm not a theoretician by any means of imagination, but I just had one query. I mean, when you do this strategy on optical interferometers, you are sort of using a beam splitter in order to sort of, simulate damping or something like that, using the fact that a beam splitter will reflect and transmit. Suppose you were doing this for atom interferometry, then would you take the atomic absorption coefficients or the transition matrix elements or something like that and just reproduce this theory, or would you try a different approach then? I mean, where you actually have atoms absorbing photons and you know exactly how they sort of would, react?
Yeah, so I think there are two ways of doing that. And, just thinking quickly about your question, which is a very good question. So you can either look at the detailed loss mechanism, okay, which, as you mentioned, I mean, you look at the Hamiltonian involving the interaction of the atom with the photons. So in this way, you have closed the system, and you can do it. Okay, so that would be the most natural way of doing it. Okay, the most natural extension. And the other would be, of course, to imagine some atomic beam splitter, but that would be going too far.
Yeah,
okay,
exactly.
So my first try would be just to include the interaction with the photons and close the system in this way, and then calculate the quantum Fisher information for the whole thing. Now, of course, one should just saying that is not enough. Okay, you have to actually calculate it and see how good is your result. Okay, and if it's bad, then you have to imagine another way of extending the system. But that's the most natural way of doing it, of course. Sure.
And suppose you had like two ions, qubits or something like that. And do you think that this could be used for measuring decoherence or, how they're entangled in some such way? I mean, some kind of coupling with the whatever. I mean, as an experimentalist, suppose there is a bit of vacuum issues and you have collisions, and can that also be factored in? I mean, things which would sort of cause one ion to behave a little differently from the other, so that you have issues in the the coherence and whatever entanglement and all that.
Sure, I have not done that. That could be possible. And again, you have the extended space would include the ion plus the space corresponding, say, to the photon emitted by it or any other reason for the coherence. Okay, so you would have to extend the space and calculate the quantum Fisher information for the whole thing. That's the first idea. Maybe other ideas should come. And for instance, you extend the space, but then you might imagine to do something to the environment. You have
exactly.
the photons coming out. You might want to apply, depending on what you are measuring, you may want to apply, say, phase shifts to the photons, or
scattering, some scattering sort of things.
Some scattering, something like that, so that you have some degree of freedom, some variational parameter that would allow you to minimize this quantum Fisher information for the whole thing. Okay.
And so how good are the matches with experiments on this? I mean, for example, have you been able to see things that, matches with the LIGO measurement or something like that, where you do have these extremely, very sensitive measurements?
Sure. No, we have not done that. We have done, however, numerical calculations for some of the systems we have considered. Actually, I have one slide for that, but I'll just tell you in general. what we have shown is that, for instance, for the optical interferometer, in which we apply the phase shift to the environment, and that phase shift was a variational parameter. What we calculated numerically the quantum Fisher information for the optical interferometer, itself, for the open system. You can calculate it for a number of photons going up to 100, say. And what we have shown is that our bound was indeed very, very close to the numerical result. We have done this for other problems as well, problems involving diffusion, for instance. And again, our result was very close to the numerical results. By the way, diffusion is an interesting problem, because if you have, say, one mode, could be a harmonic oscillator, but one mode of the field subject to diffusion, not just dumping, diffusion of the phase, then you know how we close the system. We had a mirror, and the mirror was vibrating, and it produced this dephasing, and that took us very close to the numerical solution. So, I find it, as a toy, I find it very fun, because, you have to imagine things and be creative, actually, to imagine these extensions. And that's what we have done. But of course, doing that for LIGO, we have not done. And the reason for that is that you need lots of information, because there's several sources of noise there. So it is a difficult problem. It is a difficult problem.
So are you guys actually doing some experiments in your lab in order to validate with experiments? And so what kind of experiments?
Yes, so one of the experiments is this one I mentioned. Experiments we have done all other experiments on entangled states, and and I have not mentioned them here because they are not specifically on quantum metrology, but we have done lots of experiments on that, looking at the coherence of entangled states. And that was some years ago.
These are like for ion traps, or these are where, I mean?
Well, it's a similar problem, because we can use polarizations of light as qubits, and also you can use paths as qubits. The path in an interferometer, right? It's either the photon is either here or here, so it's a qubit. And we have done lots of experiments on that, on the coherence, loss of coherence of entangled states, and including more than 2 qubit entangled states.
What is the maximum you have gone to?
Well, we have 4, because you have to you have these spatial qubits, and you have the polarization qubits as well. So each photon can have 2 paths, and so it's 4 qubits using spatial and polarization degrees of freedom. And these were nice experiments, published in nice journals, and that was some years ago. But more recently, we have done experiments on metrology. And the experiments, the recent experiments we have done is on this, is measuring the tilt, the small tilt of a mirror in a Mach-Zehnder interferometer.
Wow. And like what, when you say it's small tilt, it is like microdegrees or millidegrees, or what are you sort of?
Yeah, well, for
are you looking at just the phase, or
millidegrees?
Millidegrees.
And actually measure them. It's quite interesting, because we have this Mach-Zehnder interferometer, and we measure we send the twin photons, and we have in the incoming door of the Mach-Zehnder interferometer a selection process by which vertically polarized photons go one way, horizontally polarized photons in the other way, and so they have different paths. And at the exit door, we show that just by measuring the polarization of the photons, we get information about the angle. And the polarization measurement is a very simple polarization. It's a simple measurement. It's much, you can have information about the tilt of a mirror by sending a laser beam. And then you see how the
polarization is tilted.
And you see how the laser beam is tilted.
Not
just polarization, that's a laser beam.
Exactly.
But of course, the problem is that if you want to have better resolution, you have to increase the distance between the wall and the mirror, But if you increase the distance, the laser beam, the cross-section gets larger. So you lose you lose information too. And so instead of measuring the deviation of the laser beam, we just measure the polarization of the exiting photons. And that gives us, we show that gives us information about the angle. Okay, so
this can also probably be done by beating it with a beam which has the unchanged polarization and doing a weak measurement or something, right?
Very good. Yes, sure. That can be done in that way. And in fact, we have also analyzed weak measurements. You can probably
see how good it matches. Yeah. How good it matches with your technique.
Right. So we have also analyzed weak measurements, but in a quite general way. Okay. So we are comparing weak measurements, the resolution obtained with weak measurements, with the quantum fission information for optical interferometers.
That is super. That is another talk.
And yeah. And then what we showed is that weak measurements lead to a resolution which is always worse than the quantum fission information. However, under some circumstances, for instance, for very small angles, they get very close to the quantum fission information. Okay.
So have you published this?
Yes, that was in Physical Review, Physical Review A. Okay.
Oh,
it's a long paper.
Is this recent or
Review A? Well, it is. Let's see, not so recent, but I can just wait a little bit because I can take a look at this now.
Yeah, maybe you can put it in the chat so that because
I can put it in the chat.
Colleagues here, yeah. So he does.
I can actually send you the paper afterwards if you want. But anyway, so
that's also nice.
And also the slides. Okay, I can send you the slides. So,
yeah, absolutely.
I have a question, Oyan.
Okay. While I look for the paper, let's see. Just a moment.
Yes, sure.
Okay, I found it. That's a paper from in 2017, Physical Review A.
Too far back, 3 years, 4 years.
Yeah. So it's achieving metrological precision limits through post-selection.
Yeah.
Okay. And the one I mentioned now, quantum enhanced sensing from hyperentanglement, is from 2018.
Okay.
And in 2020, we have another paper from our lab, which is, it was rapid communication. And it is also on using quantum fission information and so forth, and with this Mach-Zehnder interferometers for finding the tilt angle of a mirror.
Just quite nice.
And now we are doing
other comment in the chat. I think so. There is a comment by Sham Sahu saying that squeeze state can even increase precision of measurement even if it is at its limit.
Sure.
So that is I think that is.
I have a small question. Professor Davidovich, your group was the first one to show entanglement sudden death. My question is that does it look like a phase transition, or what is the physical origin of that sudden death?
Okay, very good. It is similar to a phase transition, but it's not a phase transition, okay? Because, of course, you are dealing with entanglement, say, of two photons. So you don't have an infinite number of particles. You just have two photons, okay? And the idea is the following, that it's counterintuitive in some sense, because, if you look at measures of entanglement, they depend in a nonlinear way on the density matrix of the system. Okay, so it's a nonlinear function of the density matrix, and you can show that entanglement may disappear if you have two entangled systems. You can show that entanglement may disappear even if you still have coherence in the system. Okay. Now you may say, come on, this depends on the entanglement measure you define. But no, you can show that, every possible definition of an entanglement measure must vanish at the same point than the others. Okay? Because you can show that at the very point where you have entanglement sudden death, that means entanglement dies before the system decays, before the atoms decay, before coherence is lost. So at the very point where the entanglement dies, the system becomes separable. Okay, so if it's a pure state, that means, of course, for a pure state, that would mean that you get a product state. For a mixed state, that means that you have a sum of products of density matrices of the two systems. And you can show that at the very point, the entangled state becomes a separable state. Okay, and that comes, so the physical reason for that is that entanglement is actually a quantity that depends non-linearly on the density matrix. And it gets to points like that. Yeah, we have shown experimentally the sudden death of entanglement. Yeah. There is also Sumantra Das has a chat here. Let's say, I'm not sure. Yeah, let's see. You have pointed out in the previous conversation that while increasing the length of a laser, there is chance of loss of information. Will the same situation happen if we consider the photon is passed through a material like optical wire, where the reflection takes place from coating? Okay. So not necessarily, okay. Why? Because if you have this coating in the optical wire, and if there is no loss, I'm just talking about reflection. The reflection is such that, of course, you don't, at the end, you don't lose. I mean, you keep the cross section of the beam with the same, the same distance. Okay, the same length. Okay, if you have an optical wire, so the cross section will not increase because you have an optical wire. But then the challenge would be to measure the tilt with this optical wire. Okay, so we have to imagine how to do that. And it may be possible for very small tilts. You have different angles of injection of the field into the optical wire, and that would overcome the problem of increasing the length of the cross section. So it is an idea, but we have not tried that, and we have not even investigated that theoretically. And Sumantra, you should do that.
So when he says optical wire, it's probably a fiber, right?
Fiber,
so
yeah, that's what I understood.
Anyway, it's supposed to be TIR, right? So losses because of TIR, reflection losses should be absolutely minimal. So unless you have...
Yeah, that's it.
Right, because the coupling itself is due to TIR. So,
right,
so
that's true.
You may have coupling losses, but whatever you put inside the fiber, that should be extremely lossless. I mean, very so. Especially for single mode.
Yeah, so it would be interesting to compare that, say, with these other ways of measuring tilt, mirror. I mean, the tilt of a mirror by using, for instance, by measuring.
But Luiz, what would you say is the equivalent of tilt here? I mean, because tilt is actually,
very good. It's like that. You have the optical fiber, and then you have the beam that comes out of the interferometer.
Angle.
That angle is different, so you should be able to measure that angle. Yeah.
So basically, the cross section of the beam that comes out.
Yeah, but then what I can say to Sumantra is the following. Just think about it. Is that so in order to avoid this increasing of the cross section, of course, you have to put the input door of the optical fiber very close to the outgoing field of the interferometer, right? So you're measuring close to the interferometer, okay? Now, and then again, you are measuring the displacement between the two beams. And then you fall into our condition where we show that measuring the polarization is better than just measuring the angular displacement of the beam. So
optical fibers are more complicated as well, right? Because you need a coupling lens or something. So without that, you will not get anything. So that just gets more complexity to the problem.
That's true. So you see, in some way, but what my point is that in some way you don't even need the optical fiber, because at the end you'll be measuring the angle between two beams very close to the interferometer. So you you don't need an optical, unless you want to make for some experimental facility, say, you can only do the measurement far away from the interferometer, but usually it's not the case. You are there. And, okay.
Okay, so yes.
Yes, actually, that means like while improving the quality means the optical communication means in order to improve the.
Is this Sumantra, by the way? Can you introduce yourself?
I beg my pardon. My name is Sumantra Das, and I am a undergraduate bachelor student from NIT Raipur, currently in metallurgical and materials engineer. So,
that is great.
Very good.
Actually, while I was listening the last conversation, so my idea means I was asking, so in order to improve the optical communications, so we have to consider the trade-off between the amount of TIRs happening within the lens, within that cross-section, as well as the length of the distance traveled between those TIR intervals. So if we can consider the optimal the trade-off or optimize both the factors, then we may improve the optimized level of communication.
That's true. If you want to, but that's the point. So if you want to communicate that tilt to some place very far away, you can use it. But if you are just interested in measuring the tilt without any limitation in the proximity, say in closeness to the experimental apparatus, then you don't need the optical fiber. But I agree with you that if you want to communicate it with some place outside, then you can use the optical fiber, yes, for communication. Very good.
Sir, will you kindly point out some current applications of this technology or this idea within the realms of the material science in the modern understanding? Means how can we incorporate the ideas in the material science?
Okay, good. That's quite a challenge. Let me give you one example, which is related to something I mentioned before, and. So I actually have two answers to this question. The first answer is to you, Sumantra, is that, I gave you the basics, and now I challenge you to think about applications to material sciences, since you are working on that, okay? So that's the best answer I like to give to a student who asks me a good question, okay? So just think about it. And if you have some ideas and you want to communicate further with me, let's talk, okay? So that's one thing. But the second answer, more direct answer. I mentioned to you the measure of the damping constant of a material, right? And that's especially good. We showed that in our paper for thin slabs of material, okay? So if you have a thin slab of a transparent material and you want to have some information about the damping constant, which should be very precise information, that could help, okay? Now, you probably could extend this to other kinds of investigations on the material. For instance, possibly some resonance frequencies of the material. I'm just, saying like that, okay? It's up to you to think if it's viable or not. Also, as we showed in our paper, that's a way to measure the temperature of that thin slab, okay, by using single photons, which are, of course, not very little invasive on the material, okay? That's a very weak field that you use to investigate the material. So that's a possible application. You can also have... I would
say, Luiz, even things like, measuring surface roughness and all of
course.
That also is useful because that would sort of change the tilt to something if you have, extremely wavelength level things.
That's the very first, I think the second slide I showed you, which was precisely that, okay? You have there we had a laser beam on a mirror, and there is some, I don't know, what pointer here attached to the mirror, and that was going through the surface of some material. So the mirror was doing like that, and that would allow you to map the roughness of the surface of the material. That's another possible.
So this is like an optical AFM or something, right?
Right.
Virtually an optical AFM type.
That's true. That's true. So we're measuring the tilt. And by the way, I also showed you some other systems that are now doing that. You know, they are actually doing that. You have these nitrogen vacancy magnetometers, which can also be used to map the surface of some material. These are really spins of these nitrogen vacancies that are sensitive to the magnetic fields in the surface of the material. So you can use that to map the surface of the material. That's another application, another possible application. And that goes up to the microscopic level because, as I showed you too, you can use a single atom to map the structure of a biomolecule, for instance. Okay, so if you think about the materials, there are lots of possible applications, and I'm just mentioning those that are related to either sending light through the material or looking precisely at the tilt, small tilt of mirrors, for instance, or to forces exerted on single atoms, for instance, that you might be able to detect. So that's these are some of the possible applications.
Thank you very much, sir. But actually, the idea just now which you mentioned regarding this optical AFM, Professor Ayan Banerjee had already mentioned it. But the idea yesterday, while there was another talk regarding the means increasing the time between time of the time calibration and all that. So in the same way, in this case, if I also try to map for the del X, means for a better del X, we will be losing the momentum. Means del P value will be high. The error of momentum associated with the photons will be high. So won't that measurement cause a trouble?
You are right, that may pose a problem. However, I should say that, people are using these magnetometers, which are quantum magnetometers. They're using them now. They're using them now. They are using them with these nitrogen vacancies. There are recent, in the list of papers I gave you, there are papers from 2020, I guess, 2019, that actually demonstrate experimentally these nitrogen vacancy magnetometers. You have also even the mapping of the brain with quantum magnetometers. You are measuring very weak magnetic fields, and with that, you have a precise mapping of the brain. So I do believe that, one must consider these effects that you have mentioned, but, somehow people are, that goes to the practical implementation of that, which is very important. But I see that people are doing it in this way. So maybe you'll be able to tell me more about that, and I can tell you about it. Okay.
But do you think, the error in momentum space, why should it affect? Because I'm not concerned with that, right? I'm trying to find out my sensitivity is in the delta X. So, I may sacrifice some.
If you use spins, or if you use spins to detect magnetic fields, for instance, then you are in the angular momentum space. Okay. So also I should say that rotation. How do they call it? There are accelerometers, and there are also devices to measure rotations. Okay, and some of them are measured based on even the coupling of the electron spin with the nucleus spin. So it's just the idea of the classical physics experiment that students do, the angular momentum experiment, that you turn the wheel and then you turn yourself. So this is being used in quantum gravitometers. So and then angular momenta are very important in this way. Okay.
Thank you very much, sir. Thank you. It was indeed very helpful for for me. Thank you very much.
Thank you, Sumatra.
Okay, so we have considerably overshot our time, but I don't think that was. I think we enjoyed it quite a bit. This conversation, at least for me, was.
I enjoyed it too.
So, it was very, very nice. Finally we had something to discuss. Which is happy and which is with physics is so nice in these days, especially. So I would. Yeah, thank you so much, Luiz, for this.
Thank you. Thank you for inviting me. Thank you. Congratulations for organizing this school. I think it's a very important
hopefully we'll
event.
have you around sometime. 10 years. You have not been in India for the last 11 years. It's a long time. I don't know. Did you come after 2010 to India?
I came for other reasons. Let's see. No, actually, very, very good question. Maybe that was the last time I went to India. Yeah, I came before that.
So that is so surely it is due.
It is due, yes.
Have you back?
I came because of TWAS. I went to India because of TWAS.
Yeah. That was even before that.
Yeah.
It was before that. That meeting I think was happening just before this thing. It was in Bangalore probably. Was it in Bangalore?
Right.
The TWAS meeting?
Yeah, I have to remember that. Yeah. No, actually, I was in a meeting in New Delhi. Meeting in New Delhi. That was even before.
Okay.
And it was an amazing meeting. I got the TWAS Prize of Physics at that time.
Yes.
And my philosophy then, as now, as was with my wife, is that since life is short, we should spend the prize immediately. So
did you take some vacations somewhere?
Yeah, I took some vacations in India, which was amazing. A fantastic trip in India. And I went to Rajasthan. Amazing trip.
Hopefully
I really
those
enjoyed
days will be back again. Now,
hopefully.
The last time I have traveled is, I don't even remember now, 2 years gone probably since I have last traveled. It's nightmarish actually. February 2020 was when I last traveled. So it's like 1.5 years.
Me too. I was actually 2020, January, February, I was in the United States.
And February was when I went to IIT Delhi. So after that, it's just been one.
Right.
I cannot imagine, right? I mean, I don't remember ever since the last 12 years sitting down for 2 years or 1.5 years.
Yeah,
Anyways,
that's amazing. I start wondering how the world outside is like, Exactly. I can see it only through TV.
Right. So today, actually, I went to the institute after 2.5 months. So that itself is remarkable, because I am recovering still and it's horrible. But
our institute is still closed.
There is lockdown. So we are partially open. I mean, the labs are not fully functional.
I see.
I met my students physically met them after such a long time. But our generation will be remembered in the history of humanity, I guess. That is the price we pay out of our sacrifice. The COVID generation or whatever. But however, this curse will probably lift in some time and we'll meet each other physically instead of seeing small pictures on this Zoom screen. And,
very good.
Just wish that happens as quickly as possible.
Very good. So now, would you like me to send you? Would you like me to send you the slides of this presentation?
Absolutely.
Okay, good.
That would be great.
Okay, very good. Okay, and also in my homepage, you can find some of the papers I mentioned today. Okay,
it's fantastic. So Prashant, you want to say something?
Yeah, I just wanted to say that we'll work out this paper which you told us to work out with Professor Agarwal. I'll ask students to work it out as a homework.
Very good. Very good. Great.
Okay, thanks to you again. Thanks to the students for attending.
Thank you to the students as well. Bye. Thank you for the nice questions.